All right, next lesson. The derivative of the general logarithm. The general logarithm we will write as y equals log base a being any real number greater than 0. So we have a log of base a of x. This is the general logarithmic statement. This statement can be rewritten as a to the y is equal to x. If we were to take the derivative of this, we would have to take the ln of both sides, so that you have y ln a is equal to ln x. Once we do that, we can take the derivative of y with respect to x, so that you have ln a is times dy by dx is equal to 1 over x, which is the derivative of ln x with respect to x. Once we do that, we can take dy by dx equal to 1 over x ln a. So we can now, once we're given this logarithmic statement, all the way, we can find the derivative by writing dy by dx, so the derivative of y prime, is equal to 1 over x ln a. That is the derivative of a general logarithm. Now, if we have f at x is equal to log a of some function g of x, we can take the derivative of that by rewriting it, and it turns out that our derivative will be g prime over ln a times g of x. So 1 over g of x times ln a multiplied on the numerator by g prime of x. So g prime of x over ln a g of x is the derivative of the general logarithmic statement. Let's go on to an example, or a few examples. You're asked to differentiate y equals x squared ln x and y equals log x to the power of 5 plus 3. For the first question, you're asked to find the derivative. That's pretty easy. We use the product rule, which is 2x ln x plus x squared times 1 over x, and the derivative is going to equal x times 2 ln x plus 1. And I know we've seen this question before, but remember that the reason why we common factor is sometimes there's an extension to this question. You may not be given this directly, but you may be asked, for example, to find a max or min value. In order to do that, we set the derivative equal to 0. We find the values, and then what we would do is do a t-chart. If you're asked to find a max or min, you must do a interval chart. You find the interval, the test point, and the derivative. And you find out that the interval goes from negative infinity 0, 0 to e to the negative a half, and e to the negative a half to infinity. We find the test points. The test points are negative 10. And that does not exist. Why does it not exist? Because you cannot take the ln, for example, the ln of a negative number, because e to the what equals a negative number, and that doesn't exist. E has a base of 0.718. That's what e is equal to. To the power of something equals a negative number. Not possible. So that does not exist. Then we test 0, and we find out that 0.1, sorry, not 0, but 0.1. We find out that the derivative is decreasing. Then we test 10, and we find out the derivative is increasing. So at that particular point, e to the negative a half and whatever the value is, it will be a local minimum. Now let's look at the second one. This is just an extension, folks. This part right here has nothing to do with the original question. This was given as an extension for you to see how important these values are. Let's find the other derivative. Y equals log of x to the power of 5 plus 3. what you do is you want to find the derivative. The derivative is 5x to the power 4 over x to the power 5 plus 3 times ln 10. Why ln 10? Does anyone remember why it's ln 10? Hopefully you remember that the base of a general log, of regular log, is 10. So you have to remember that it's going to be the inside, the denominator is going to be the inside times ln of the base. All right, let's look at a tougher question. H of x is equal to 3 to the x ln x. Well, h prime of x is equal to 3 to the x ln 3 ln x plus, now where did that come from? Well, we're finding the derivative of this, which is 3 to the x ln 3 times the second function plus the first function times the derivative of the second function. And once we do that, we can common factor, and you're left with ln 3 ln x plus 1 over x. And if you were to do this further, you could pull out an x and then make this question a little bit easier. All right, that's the end of the lesson, folks. Here's the homework. And now we're going to look at an example. But before we look at any more examples, I want you to check the review. I want to review all the different logarithms we've learned. First derivative we learned was e to the g to the power of x. So that was our Euler's number. So y equals e to the gx and the derivative of that is equal to g prime of x times e to the g at x. Next, y equals ln of g at x, so the ln derivative, and the ln derivative was y prime is equal to g prime of x over g of x. The next derivative we learned was the general exponential, so a to the power of g at x. That is equal to, the derivative of that is equal to g prime of x times a to the g at x, ln a. Don't forget that ln a, folks. And the last derivative we learned was today's, which is y equals log base a of some function g at x. The derivative of that is equal to g prime of x all over ln a, so ln of the base, times g at x. All right, that's the end of the review of the different derivatives that we've learned of this whole section before your quiz. All right, take care. Have a numerical night.